Thank you very much. It is such a pleasure to be here. It really is. Thank you so much for inviting me. So the question that Ard asked me to talk about is this one: what a teacher should know about computing. I think this is a really good question. Ard asks good questions, but what sort of question is this? Is this a question like, what should a teacher know about reading and writing? Well, quite a lot, really, given that you can't really become a teacher unless you know something about reading and writing. Is this a question like, what should a teacher know about mathematics? Slightly different question. You know, some of us are probably very, very good at mathematics, some of us maybe not so good at mathematics, but we all kind of have to be able to use mathematics to a greater or lesser extent in our professional roles as teachers, and some of us have a job teaching mathematics to others. Or is it a question a little bit more like, what should a teacher know about music? Many of us might really enjoy music, but would perhaps feel a little bit reluctant teaching music to a group of 30 young people sat in front of us, and many of us probably don't have the specialist knowledge to take charge of that part of the curriculum or music that happens in a school. So what should a teacher know about computing? What does that mean? Is it about the use of technology to enhance education? Is it about the use of computing across the curriculum? Or is there perhaps a little bit more to it than that, something which requires a certain degree of specialist knowledge? Well, let's start at the basic level of the use of technology in our professional life. Some knowledge of computing seems kind of essential to be able to use technology in a way which enhances, extends, enriches the experience of our students, of our pupils. We've been using technology in education right from the very earliest days. I don't think we'd be entirely comfortable declaring language to be a technology. But language is what sets us apart as a species, that we don't have to have the experience ourselves. We can borrow other people's experience through the medium of language, that by listening to other people, that by talking about ideas, we can take their experience and make it something of our own. And language is, of course, the medium through which we communicate. And my apologies to you all that I'm having to communicate in my language rather than yours. That's for us. Okay, but writing, of course, makes that idea of language something which happens across time and across space. You no longer have to be I can take this off and talk to the back of the room. Okay. It's okay. Right. Where was I going? Yeah, so the written word takes language and makes it a permanent and transferable thing. And education changes as a result of that. You can now learn through people who've written down their ideas, who've stored those ideas that they have and communicate them through the medium of the written word. Then a few years later on, we take the idea of education and formalize that within the institution. Here is Raphael's fresco of Plato's Academy. And we have this lovely sort of detail at the bottom left-hand corner there of Pythagoras writing the book, probably about right-angled triangles, and the student at his feet there with something which looks very, very similar to a tablet-like device. Space Invaders or Galactions, he's playing on that. I worry about the gentleman with the beard at the back there taking notes. Is he the education inspector checking that the lesson is being conducted according to the rules there? The textbook comes later, and one of the first uses of the printing press was that democratization, well, semi-democratization of the written word in a learning context, of taking the ideas of how to teach this, how to understand these ideas, and making those something which is accessible to anybody who has the money to buy the book and can read, can access the content there. But the printing press, well, as I said, one of its first uses was producing textbooks. Early example of a mathematics textbook there on the screen. We then, of course, put technology into the hands of our learners. And again, the form factor will be familiar to you now. We have a device here on which the learner can record their own responses to whatever the content is that's presented to them. And it's the first schools that made use of slates as a learning technology. The arguments were, well, firstly, this would save printing costs because you could have the slate only, you needed one of those. And that also you'd be able to tell at a glance what the young people, the children, were doing during the lesson, because you could just scan their slates. You could see evidence of progression, evidence of achievement. And similar claims are made for similar devices these days. The web I see as a transformative technology. Yes, the printing press made it possible to take one expert's ideas and get those into the hands, into the minds of vast numbers of people in a way which before that had been impossible. The web makes reverses the direction. It means that all of our ideas, all of your students' ideas, can reach an audience of potentially, what is it at the moment, 3 billion people. If you're getting 3 billion hits to your school blog, then give us the URL, please. That's going really well. So the web changes this. If you've got access to the web now, if you've got the time, if you can read, then you can pretty much teach yourself anything. Okay, you have to have the motivation as well. You have to have the will to learn this. And I think there remains a role for teachers in that process. But the web has transformed education. It may not have transformed schooling yet. But there is much, much more to education than merely what we do in schools. So the web is transformative technology. And of course, now the web is something which is entirely portable. Put your hand up, please, if you've not got a device with which you can access the vast quantity of the world's knowledge there with you in the room. And the same would be true of many of your students in school. We can answer those questions now. We have access to knowledge. And that, again, I see as transformative for education. So some understanding of these technologies, I think, is part and parcel of our role as teachers. Is there more to it than that? Papert, writing in 1980, in many schools today, the phrase computer-aided instruction means making the computer teach the child. One might say that the computer is being used to program the child, which is fair enough. We have lots and lots of lovely drill and practice maths games, spelling games online now. Sitting a child in front of a computer and expecting education to be transmitted into their brains via the technology. Move it up? Okay. I still think this is too boomy. Shall we try that? I'll talk loud. Okay. Just put it on the desk. Does that work? No. Is that okay at the back of the room there? All right. Does anybody want me to use the microphone? Okay, fine. Right, say if you do. Right. In Papert's vision, the child programs the computer. In doing so, acquires a sense of mastery over a piece of the most modern, powerful technology, establishes an intimate contact with some of the deepest ideas from science, from maths, from the art of intellectual model building. The argument is not so much the computer being used to teach the child as the child teaching the computer how to do something new, the child taking control of the technology. And what we're trying to do around computing education is flip this. Instead of access to content, it's putting the child in charge of the technology as somebody who can take charge of this and learn through that experience. So this isn't so much about education technology as technology education, an understanding of the technologies on which we've come to rely. Why would we want to do that? Well, in part because this is pervasive. Our world is a digital world now. Digital technology, right from before a child learns to speak, it is part of their environment. They grow up into this world. I am not claiming a child is born knowing how to use an iPad or how to type. I don't believe that there is such a thing as a digital native. But I think for my daughter on the slide here, she learnt how a tablet worked before she learnt to speak. She will never remember a time when she couldn't use a touch screen device. I'm not saying she knew how to change her privacy settings on it then, but it was part and parcel of her environment before she acquired language. She'll never remember a time without that. So we meet children where they are. This is part and parcel of the world in which they inhabit. And some understanding of that, I think, is as important as some skills in being able to use that. There's more to it than that. It's not merely about the technology which we use. There's something about computer science which seems fundamental to the nature of reality. That in our lives, in our world, in our universe, some problems are easy to solve. Some problems are, in fact, impossible. We cannot find a solution to these things. And in the middle, there's a whole class of really interesting problems which become easier to solve if we think about them the right way. This seems something which is fundamental, at least as fundamental as physics. Computer science as the zero science is something which captures something about the nature of our world. making that part of students' experience. Why should we teach children about technology so that they can get jobs? Well, yes, but we don't teach children about poetry so that they become professional poets when they grow up. Some of the children who you teach will become the software developers, the computer scientists, the programmers of the future. But this is part and parcel of all of their worlds. The argument that works with our ministers was one about vibrant UK software industry, game industry, fintech industry. We needed a stream of young people coming through university able to write software. I think it is an important argument, but it's not, for me, the most persuasive argument. We are preparing our children for a future which is entirely uncertain. If you think digital technology will play a less important role in their future than it does in our present, please put your hand up now. Okay, all right, so we've not yet got to peak tech. And preparing students for this future involves not merely being able to center text on a PowerPoint slide, important as that life skill is, but some understanding of the unchanging principles on which this technology is based. That's the best preparation. And I think there's a very, very persuasive argument around what we're now calling computational thinking that Papert was alluding to on the slide earlier on. That through the experience of taking charge of a computer, of writing computer programs, your way of thinking about problems changes. You become less interested in finding the solution than you become in finding a way to find the solution, of a way to automate the solution of problems. The way you look at problems, the way you look at systems changes when somebody teaches you about abstraction, or when you have the experience of, okay, I can put that detail to one side, I can hide that complexity inside a function definition and look at this at a top level. Your way of thinking about systems changes. And so that is part and parcel of what technology education, digital literacy should do. In the English curriculum, we now call the subject computing, and it's worth talking a little about what we might mean by that and why we've made the change that we have in our curriculum. The direction of travel is from one of consumers of digital technology and content to creators of digital technologies, technological artifacts, content. When we look at young people moving from primary to secondary school in England, we saw them as pretty good at using a range of technology, pretty good at communicating using a range of digital tools, sometimes where they're not really keeping to the terms and conditions and are using them without proper permission. They could read and write in a digital domain. They were digitally literate. They could, by and large, keep themselves safe online. They knew if somebody was being creepy in an online space. They knew that there was information they shouldn't share online. They had a range of skills with which to move on to secondary education, but by and large, it could well have been magic inside the machine that was doing that for all that they knew. So we meet them there, and we take them on now to some new place, from being users of technology to makers of technological artifacts, if not yet new technologies. From yes, being able to communicate, to more than that, being able to collaborate in online space. From yes, being able to read and write, to now being able to ask the why questions. What's the business model? Why does it work like that? What are they getting out of this? From yes, keeping themselves safe, to more than that, being responsible. Typically, the problems which we had with our 11-year-olds were not about safety, they were about responsibility. Children accessing content that they shouldn't at their age, or in some cases any age. Children being horrid to one another in online space. And yes, children lying about their age and not keeping to the terms and conditions of the content that they were accessing. Is the same true of children in Netherlands primary schools? Okay, right. From having a set of skills to, yes, keeping those skills, but also now having some degree of understanding here and replacing this sort of sense of it being magic with some actual knowledge of how the technology works and how the technology is made. We followed the advice from our Royal Society in terms of seeing computing as a subject which had three elements to it: computer science, information technology, and digital literacy. I think it's helpful to think of those in terms of the foundations of the discipline, its applications to getting useful things done, and the implications of that for our lives as individuals and our life as a society. Let me give you an example of this in terms of the question, how does Google work? How does Google work? Well, you kind of just type the words in and click the button. Actually, you don't click the button now. Google starts looking as you're typing, which is kind of magic, I'm sure. So, being able to use a search engine well is part and parcel of what computing education ought to include. A child should leave primary to secondary school being able to use a search engine effectively, being able to filter the results according to date or according to country of origin, being able to tell whether something is a sponsored result, being able to decide for themselves whether a result is going to be useful. Being able to use it matters. But I don't think it's enough. How does Google work is also a really interesting computer science question. And we have to then talk about making a cached copy of the web, indexing the keywords on those pages, following the links between those pages, and using the number and the quality of inbound links in order to determine the rank of the results which are displayed. Some understanding of how it works ought really to go alongside merely being able to use it. But I don't think those two on their own are enough either. We also need to think about the implications questions. Are we too reliant on one particular company's particular product here? Is there anybody in the room who doesn't use Google as their search engine of choice? Okay, well, why is that? You work for Microsoft? So what's your search engine?
Sometimes use DuckDuckGo.
DuckDuckGo is nice, yeah. But the rest of us, and I bet almost all of the children, the pupils in your schools, are reliant on one multinational corporation's service. Never since the Reformation has one organization controlled so many people's access to information. What are the implications of that? And what's in it for Google? I don't pay to use their search engine. They don't charge me for this. They do build up a very, very detailed profile of what I am interested in. And they use that to target advertising for me so that I'm more likely to click on those little adverts there. Actually, I turn those adverts off and I never click on those adverts. Does anybody in the room click on those adverts? Okay, how do they make money there? Okay, it's you two. You two are responsible for Google's income there. Thank you very much. Okay. Companies annoying you? Google them, start clicking on their adverts. That'll cost them. Okay, so we need to think through the implications of an organization knowing so much about us. If you don't believe me, go to google.com/myactivity and have a look about the profile they've built up. I'm not going to put that on the big screen now. Okay. So we start the English computing curriculum, which is just 4 pages long, with this inspiring sentence. A high-quality computing education equips pupils to use computational thinking, this way of looking at problems, and creativity. Okay? The two go hand in hand. But there's a purpose to this. It is about understanding and changing the world. Not about learning to code. It's about understanding the world in which you find yourself, being empowered to make a positive difference to that world. I think that ought to be part of every child's entitlement. That's the purpose of education, or at least part the purpose of education, to understand the world in which you find yourself and to be able to make a difference to that world. And computational thinking is a good way of looking at the world in which we find ourselves, not just the digital world. And I think creativity is a fabulous way of making a positive difference to that world, making something that wasn't there before that makes the world a better place. We go on, though, to acknowledge that computing has deep links with maths, with science, with design and technology, and I would argue many, many other subjects on the school curriculum, and provides insights into natural and artificial systems. So what should a teacher know about computing? Well, how it relates to the subjects that they're teaching. Yes, computing is a subject in its own right, but how computer systems, how computational thinking relate to their subjects too. What do I mean by computational thinking? Generally, when you're using a computer, it's a 2-step process, okay? Firstly, how are you going to solve the problem? How are you going to get things done? So preparing the slides for today, the starting point is, what's the story I want to tell? How am I going to structure this talk? And believe it or not, I do that before I actually get stuck in to the slide software and start putting pictures together. The second stage is using a computer to help you with this. Making a video, exactly the same thing. Taking a digital photograph, exactly the same thing. What image do you want to capture? Now use the technology to help you do that. Writing a computer program is a brilliant example of this. How are you going to solve the problem? Then and only then translate it into the language of the code of the particular system that you're going to use. So it's the first step is the computational thinking bit. Jeanette Wing is our guru on this. What does she mean by computational thinking? The thought processes involved in formulating problems and their solutions so that the solutions can be represented in form that will be carried out by an information processing agent or a computer if you want to see it in those terms. How do you solve a problem so that a computer can then automate that solution? In maths, we're interested in getting to the solution. In computing, we're interested in getting a method which will get us to the solution. Believe it or not, we put this sort of thing on our curriculum for our 3, 4, and 5-year-olds. Before they start formal education, the ideas of computational thinking are part and parcel of the foundations for their learning. We call it the characteristics of effective learning. We talk about children learning to create and think critically. What does that include? It means having their own ideas, finding ways to solve problems. What does it include? It means making links, being able to make predictions, being able to test out their ideas. What does it include? Choosing their own way to do things, checking how well things are going, evaluation, changing their strategy as needed. I've shown this slide when we've had senior engineering managers from Google in the room. That's pretty much what they're looking for in their recruits. Okay, if you can do that, then you can get your job at Google. Okay, we're not kind of getting kindergarteners straight into jobs at Google yet, but you never know. Okay, so laying the foundations for this matters from a very early age. And I'm sure kindergartens in the Netherlands do exactly this. But the coding is important too. You can do this through unplugged activities. We can teach algorithms through making pizza and making jam sandwiches, and that's fabulous. But the second part of Wing's definition matters too. Being able to automate the process, being able to get a dumb machine to carry out those ideas is important. And Pappett's insight was that the children who'd learnt to program started thinking about things differently. I began to see how children who'd learnt to program computers could use concrete models to think about thinking, to learn about learning, and in doing so enhance their power as psychologists and epistemologists. There's something special about giving the machine instructions that makes you think about how you think and learn more about how you learn, as well as being able to use technology really, really well. So I come back to the question that Art asked me, what should a teacher know about computing? I think a big part of this is that a teacher ought to know about computational thinking. For Barefoot Computing, which is a professional development program which BT are now sponsoring, our telecoms company, for primary school teachers. We have very, very few graduate computer scientists working in English primary schools. I know that will come as a shock to you. So what we want is primary school teachers whose background is in something else entirely to know enough computer science to be able to teach the primary bit of the computer science curriculum well. And Barefoot Computing does exactly that. We focus so much there on computational thinking. And a key message of Barefoot is you're kind of doing this already. You're already thinking computationally. You just need to use the vocabulary, formalize it, label it when it happens. So what do we mean by computational thinking? We've got a number of concepts there, like logical reasoning, being able to make a prediction, being able to answer the why question. Child says, this is going to happen. Why do you think that? Being able to justify that logically. The notion of the algorithm, the sequence of steps, the set of rules to get things done. We do this across the curriculum. Children write instructions in first language. Children make recipes or follow recipes in cookery lessons. Children have the method for their science experiments. Children follow a particular algorithm when doing maths sums. In computing, we call it an algorithm. And we teach this, and it's something which children ought to look for the best way of doing this. And we do this in the classroom too. We have particular rules for getting ready in the morning, for packing away, for going down to lunch or whatever. A computer scientist takes a big problem and breaks it down into smaller parts, and we do this in curriculum as well. We have a big curriculum to teach. We break it down into smaller parts. We break our topic down into individual lessons, our individual lessons into individual activities. We look for patterns. We generalize an effective way of getting things done. Introduction, main activity, plenary is something which many English teachers will follow. We manage complexity through the mechanism of abstraction, of not ignoring the detail, but setting it to one side, of putting it inside a box. Yes, you can look into in the box if you want to, but you can rely on somebody else to have done that. I did 3 years as a head teacher, and school leadership is very much about managing that complexity. I didn't need to see my colleagues' lesson plans. But they did want to see their medium-term plans, what they were going to do over the course of the term. I could trust them to deal with the detail, and I could look at that from a top level. And yeah, we need to check that what we're doing is kind of working. So as well as those concepts, we think computer science programming has a number of typical approaches as well. I think these are also very, very effective across the curriculum, not just in computing lessons, of tinkering, of playing, experimenting, having a go at things, of making something. Again, Patrick's great insight of children learn best, not merely through play, not merely through conversation, but through making things to show to others. Of fixing things when we go wrong, and we think here of Dweck and the growth mindset and seeing mistakes as an opportunity for learning. Of persevering when things get hard. And yes, of being willing to work together. Software gets written by large teams of people with a common purpose, not by individual coders sitting in front of a dark screen. Lovely activity to illustrate at least some of this is the think of a number game. So I'm thinking of a number between 0 and 127. Ask me some questions. And we could go, is it 0? Is it 1? Is it 2? We could just randomly guess numbers. But the computational thinker will think of a strategy for solving this as quickly as possible. Is it bigger than 64? Is it bigger than 32? Is it bigger than 48? And identify that sort of divide and conquer approach. A systematic approach to solving problems is what we're looking for in computational thinking. So as I say, the random guess approach, slow, really inefficient, and really hard to guess randomly, believe it or not. Try it sometime. The systematic linear search, that's slow, but it will get there. And the divide and conquer binary search approach, so much more efficient. You're probably teaching these strategies already, certainly if you're teaching computer science up at upper secondary level, but probably below that too. Some of you will have taught children how to use a dictionary. Do you teach them to look at the first word, look at the next word, look at the next word, and continue through the dictionary until they get to the word they want? I hope not. It's a really slow method. Just open the dictionary randomly and hope, keep doing that until you get to the word. No, open it halfway through, open it a quarter of the way through, open it 3/8 of the way through, and identify the word by dividing and conquering. There are other methods that apply in this case, but we teach this. We don't label it a divide and conquer binary search algorithm, but perhaps we could and start developing. Where else would you use a strategy like that? Finding a book in a library, that's another similar place. Where, going randomly to shelves is not an efficient method. So the algorithm stuff matters, but the coding stuff matters too. For me, the equation is a simple one. Programming includes thinking of how to solve the problem and then translating it into whatever language the dumb machine can understand there. So what do I mean by an algorithm? It doesn't have to look like a flowchart, but here's an algorithm for you. Anybody used an algorithm like this? It's Skinner, it's behaviorism, it's stimulus, response, reward. We do it all of the time. A tables test, spelling test. I'm going to ask you a question. If you get the answer right, I'll say, well done, give you a biscuit. If you get it wrong, then let's have another go about this. So we have there an algorithm that we follow. Will children recognize this as an algorithm? Yes, if you tell them this is an algorithm. Much of the educational software which we're using, which we're buying, we're subscribing to as schools, follows exactly this method, okay? It generally looks a little bit more jazzy than just, question, question, question. But typically, at its heart, it's questions, responses, some sort of reward structure. We can write code to do this. So here's Scratch code to do exactly that. And we have a number of features of the program on the screen here. So we have a sequence of instructions, and Scratch works by following sequence of instructions. Any functional programmers in the room? Okay, functional programmers may have a problem with this, but we'll leave that to one side for now. So we have, one thing after another. We set up a variable at the start. The score is initially 0. We're going to do this little bit of the code 10 times. We pick a random number between 1 and 12. We pick another random number between 1 and 12. We label those A. We label the other one B. And then we knit together a question. What is the first one times the second one? And wait. The student types in an answer. If they get the answer right, then it says, well done, and increases the score. If they get the answer wrong, it says, think again. Okay, and we go round the loop 10 times. As I say, much educational software essentially is this algorithm written, perhaps in a more sophisticated programming language. But if by the end of primary school a child can write a program like that on their own, And that's ticking the boxes in the English curriculum for computing. And that seems a reasonable expectation. Getting to that point in a building block-like language like Scratch independently seems something which pretty much all 11-year-olds can achieve for themselves. It's a lovely programming language. Doing it in Python, here's the same program written in a text-based programming language called Python. This is harder. Reading this code, if you've never seen Python before, is within your grasp, believe me, okay? You can figure out what this does. I can ask you how would you change this if you wanted to make it addition, if you wanted to make it numbers up to 10 rather than numbers up to 12, if I wanted to make it a 20-question test, okay? Being able to interpret this code is reasonable. Being able to write this is hard because of what you need to know about the programming language here. So our experience is focus on how to solve the problem, use an easy language like Scratch to create those programs. Later, once they've become fluent in using a building block language, move on to the text-based grown-up programming languages such as Python. There's additional cognitive load at this point. Mastering this language is harder than mastering Scratch. Of course it is. So our inspectorate, when they say, what should a good computing curriculum look like? One of the things they're looking for is that links with other subjects in the school are productive in strengthening pupils' learning in computing. And I think this is really exciting territory of taking young people's programming skills and now starting to apply that to other areas of the school curriculum. Very, very quick examples. In mathematics, you've seen the drill and practice program, but teaching a language like Snap how to do fractions arithmetic. A child needs a really good understanding of how fractions arithmetic works in order to be able to teach a computer to do arithmetic with fractions. Up at the top here, we have finding the greatest common divisor, highest common factor, and this algorithm is about as old as algorithms get. 2,500 years, Euclid's algorithm for finding the greatest common divisor. Nobody's found a more efficient way of doing it yet. In science, modeling the spread of an epidemic or indeed the zombie apocalypse as individual agents within the model interact with other agents in the model. In art and design, trying to draw things on screen using turtle graphics, creating something which does look a little bit like broccoli or a tree. What is it about nature that has that fractal-like quality to it? Over in geography, using historical climate data to see whether there is evidence of global warming over the last 60 years or so. This is a 5-year rolling average of average monthly maximum temperatures. And you can do that data analysis by writing code. You can probably do it in Excel. In music, seeing a program as another representation of a piece of music, of the instructions, not to the musician to play the tune, but to the computer to make the music. Anybody recognize the tune? Okay, left as an exercise for the reader. Okay. And what about PE education? Well, the Fitbit, of course, but also getting Scratch to work with the webcam or with the Kinect sensor and, dancing in front of the computer to control the sprites on screen. There's so many lovely examples of that. Diana Lorillard talks about teaching as a craft. She says it's not an art. It's certainly not merely a science. It's closer to what she describes as a design science, like architecture and like computer science. And I think there are things we as teachers can learn from how computer scientists tackle problems and apply those in our domain too. So typically, in England at least, I don't know about the Netherlands enough, school curriculum is a waterfall process. The great and the good say, wouldn't it be nice if children learned how to code? Other people design a framework for implementing that vision, okay? And they generally get paid quite a lot. Other people have the job of implementing that, okay? In computer science, they're called coders or programmers. In education, they're called teachers. They very rarely get much say into either the requirements or the design phase. There may be a fault in the system there. We then test whether that's working and occasionally correct things. As I say, much of education in England seems to follow this sort of top-down approach. We've kind of realized in software engineering that that's not the best way to get software written these days. This isn't the way to do it unless it's publicly funded software procurement processes, an iterative process of start with a design, then code, then test, and then evaluate, and then redesign, recode, retest, reevaluate. Seems more efficient. Of course, we do that too. Sorry, the slides are online. I'll give you the URL later. We have this in our line of work as well. Yes, we plan Yes, we teach. Yes, we assess. But we also should step back and evaluate whether our planning and our teaching has been effective. And then replan and reteach and reassess. Keep getting better and better at what we do. Our schools minister says he would love it if teachers could laminate their lesson plans. We don't want laminated lesson plans because we only should laminate the perfect lesson plan, and I've not yet taught the perfect lesson. In software engineering, they talk about agile development as well. That the stuff on the left, following a plan, negotiating contracts, documenting the things comprehensively, focusing on the processes and tools, yes, they're important, but it's not the best way. It's not where the focus should be, and I worry that too much of education focuses on the things on the left there, when really we want to be responsive to change. We want to collaborate with our, don't say customers, say students, say pupils. We want working knowledge, and we want to focus not on the processes and tools, but on the young people who are sat in front of us in the classroom there. We can move on from agile to thinking about craftsmanship. Yes, the things on the left are important, but actually there's more to it than that. Merely being responsive to change isn't enough. We need to steadily add value. We need to have productive partnerships, not just with the pupils in our class, but with other teachers, with other organizations. And yes, focusing on the children in front of you is great, and that's why we become teachers. But actually recognizing our participation in a wider community of professionals matters too. I am conscious of time passing, and workshops beckon, but very, very quickly, what about computing for computing teachers? That's all well and good for teachers in general, but what about those who are teaching computing? According to the US CS for All Consortium, the hardest part of getting great computer science in every school is getting a great computer science teacher in every school. And this is a huge challenge for us in England. I suspect it's going to be a similar story here in the Netherlands. If you want computer science to be taught well, you need somebody in the school who can teach it well. And that is a real challenge. We've tried to address this through initial teacher training. We have generously funded scholarships for graduate computer scientists who want to become school teachers. We also have specified what subject knowledge they need in order to be able to teach computer science well, but that's not enough. You can't wait for the next generation to make it into the profession. It will take a long time for just those leaving university to fill up the spaces which we have. So we need to focus on teachers themselves, training them, providing professional development. So this is an important part of computing at school, CAS's role here. And we've grown at an incredible rate. We now have 26,000 members across England, across the UK, and indeed abroad, from very, very humble beginnings back in 2009. We're working with a network of 10 regional centres, each based in universities, combining the education department in the university with the computer science department in the university, drawing on expertise in both pedagogy and subject knowledge, but also through a network of 400 master teachers. You'll have to forgive the gender-specific language. Classroom teachers, day in, day out, teaching computer science to the students in their school, but also having part of their time to take responsibility for training, supporting, developing the professionalism of the teachers in the schools near them. It's a very, very effective and vibrant network. So yeah, outstanding computing teaching involves, yes, being able to teach well, yes, having tech skills, but also the computer science subject knowledge. For the initial phase of what we've tried to do in professional development for teachers, we've taken the left-hand side for granted. We've said teachers kind of know how to teach already. Teachers are pretty good at using technology. We perhaps shouldn't make those assumptions. But most of our teachers have lacked that computer science subject knowledge. So our focus has been very much on filling that particular gap and worrying about the other things later. So we've produced a number of free Creative Commons or Open Government License resources. You're welcome to access all of this. The slides are online and there are links from this to the slides. So introductory guides to the primary and secondary computing curriculum and the quick start guides, which Ard mentioned earlier, which is enough of the subject knowledge background to be able to teach primary or lower secondary computer science. Barefoot I've mentioned already, some fabulous, yes, guides to the concept, but also lesson plans for teachers to put that into action. How's it going? Well, back in 2014, April 2014, just before the curriculum took effect, when we did the survey, how confident do you feel teaching this new computing curriculum, a third of teachers in England said they were confident with teaching the new subject. Last summer, Summer 2016, Ipsos Mori did the same sort of survey again, and this time we got to 81% of teachers saying they were quite confident or very confident in teaching computing. So we see that as some indication of, yeah, it's kind of just about working. Last message I want to leave you with is about inclusion. Putting computing onto our national curriculum made it an entitlement for every child in the country. And okay, there are issues around implementation, but it's not just for those who want to learn about this. This is something everybody has to be taught. Yeah? It's not just for the boys, heaven forbid. It's not just those who come from geeky homes where dad or mum is interested and excited about this. It's not just for children who happen to be in privileged schools in the leafy suburbs. This is something which is an entitlement for every child in the country, like English, like maths, like music education should be. I'm sorry, I've overrun in terms of time. I'm going to be around for a little while, so there's a Twitter thing, there's an email thing, there's a website, bloggy type thing. If you want to see the slides again, bit.ly/IENI2017 should take you to the whole deck. Most of the slides have links on. Okay, thank you very much.